So we're looking at a tetrahedral carbon. It's fully saturated with all single sigma type bonds. And so this is just methane, carbon with 4 hydrogens. And when we try to set it up, showing the three-dimensional features to it, we see that 2 of these hydrogens are in the same plane. One's coming out toward you, and that's the wedge. And then the dash is the one going down. So it's a beautiful, highly symmetric shape. And so we think, well, if we replace some of these hydrogens, if we replace them with something else, like maybe a chlorine, we could put it on any position. It's still the same molecule. And then maybe we'll replace another hydrogen. And it really doesn't matter what position. I could put something else on here. And when I flip it around, I kind of get the same molecule, same set here. Now, if I want to replace another hydrogen, something else happens here. So if I replace this hydrogen here with a sort of a, what's this, a CH3 group, I have a collection of attachments here to this original carbon where I've substituted each of these H's for something different. Well, that H stays the same, but this one's different. And then this is like a whole group. I'm going to hold on to that group so we can still see that original carbon. And so with this collection of attachments to the center carbon, we start to think, hey, I wonder if we can make an isomer out of this. I wonder if we changed positions, whether we get an isomer. And so I have another one of these. I've built it the same way, right? So what I'm going to do is I'm going to take 2 of these, and then I'm just going to switch their positions. So I'm going to take off this CH3 group and this green group, and I'm going to put my green group over where the CH3 was, and now I'm going to put the CH3 on there. I just changed 2 positions. And you think, well, what's the big deal with that? Is that really an isomer? Did I create an isomer? And I take a look at this, and I think, are these different molecules? I've got the same collection of atoms, but are they different molecules? And when I look at them, I think, well, yeah, actually, I could line up the green and the red and that methyl group. I know it looks like a mess, but I can't quite line up these 2 hydrogens. And if I flip this one around, look at this. I've got 2 molecules that have a relationship here. They're kind of similar. They get the same collection of atoms, but they're kind of similar. In fact, they are mirror images of each other. Mirror images. They're not the same molecule. I can't put one molecule on top of the other and say, oh, it's the same thing. Instead, they're different by their mirror image. That's a very special kind of isomer. So we want to say a tetrahedral carbon could have an isomer if you have 4 different atoms or groups of atoms attached to that center carbon. These are different molecules. They have different shapes, different reactivities. And so we have a special name for this kind of isomer. It's a kind of isomer we haven't encountered yet. It's called an enantiomer. I know, it's a funny name, enantiomer. And it simply means optical isomer. It has some kind of optical feature and, in fact, a mirror image. Mirror image. And then we further add a term. We say that the carbon that has 4 different groups attached is referred to as a chiral carbon. That's a chiral carbon, and that comes from the Greek that means hand. Wow. Let's keep looking at these. Maybe I'll draw them. Maybe I'll say, oh, here's a carbon. And then I'm going to put like the green one. What should we call that? Maybe that's standing for a fluorine. And then I have going toward the back, I get this red one that's usually an oxygen. I don't have anything else attached to it. And then that's one coming forward. That's a hydrogen. And then over here, I have a C, and I'll just collect those 3 hydrogens there and list them. And my other one, my other molecule, I now want to say, oh, you know what? That's an image here. I'm going to say, here's my carbon. And then I have this fluorine. And then I have my hydrogen. And going back, do you see it? Going back here is the oxygen. I don't know if it's still on. Yes. And then here is the CH3 group. And it's like I could put it like a mirror here. It's a mirror image, these 2 molecules. So I'm going to play around with these terms here. A chiral carbon is a carbon that has 4 different groups. They could be individual atoms, or they could be like a whole group, a CH3 group. 4 different is the key. That makes the carbon chiral. And if you have a molecule with a chiral carbon center, then that means you can create an isomer called an enantiomer, which is the mirror image of that molecule. Mirror image. So one way we know that molecules behave like this is because the way this type of molecule rotates light, polarized light. You could do an experiment. The way it rotates light is just the opposite to the way this molecule, this enantiomer, rotates light. So experimentally, we can tell them apart by that optical effect. And if you have a mixture of both of these types of molecules, like in the same liquid solution, their effects on how they rotate light will cancel out. And we call that mixture a racemic mixture. And when you make a molecule like this, you generally are making the enantiomer at the same time. It's very hard to separate out these 2 isomers. So racemic mixture has both enantiomers. Now we have a picture here showing kind of hands, because this is another example of a mirror image. Like if you just hold up your left hand and then you hold up your right hand and you put them together, of course your hands are mirror images of each other. They look alike. There's some symmetry there, but they're not the same. Like you can't take one hand and superimpose it on the other and expect them to look alike. They don't. Their thumbs are opposite and you got different fingers there. So they're non-superimposable, but they do have symmetry in that they are mirror images. And so they can do different things. Yeah, thanks. So what kind of different things could they do? Well, if you happen to have some molecules that are involved in, say, some pharmaceutical, maybe you're creating a medicine. And usually when you create medicines, the shape and the distribution of the molecule really matters in terms of its reactivity. So maybe you have one enantiomer that kind of binds in a site in the body, like maybe at an enzyme site, and it does some kind of physiological effect. Whereas the enantiomer, the mirror image of that, may not have that effect because it just doesn't line up properly. There's a different atom placement here. It's an isomer. So this could have some consequences. So for example, here is a picture of a drug that's well known. It's the active ingredient in Aleve, which is an analgesic, naproxen. So the name of the drug is naproxen. And there's a carbon right here that we should put a little asterisk by, or a star, because that carbon is a chiral carbon. How do we know? Well, it's got an H, and then this kind of group with some oxygens there, and then a CH3, and then a really crazy group on the other side. It's got 4 different groups attached to that tetrahedral carbon. That means there's a potential of making this molecule along with its mirror image isomer, its enantiomer. And it turns out that the drug that you take over the counter, if you have a headache or something, it's formulated as one of the first chiral drugs. They only selected 1 enantiomer to put in that drug. It's a good thing because only one of the enantiomers actually is an analgesic, a pain reliever. The other enantiomer is not a pain reliever at all. In fact, causes liver damage. So you would not want a racemic mixture of naproxen to take in your pain-relieving medicine. You only want the one that is effective. Here's another example. So it's crazy how we're representing these molecules. I mean, we tend to get a little bit lazy and we don't even write a carbon that's supposed to be right here, and another carbon. But anyway, looking at this backbone structure, these look like very similar pictures, but they are mirror images of each other. Now, this one's called dextromethorphan, and it's used as an active ingredient in a cough suppressant. Whereas its enantiomer, levomorphan, that one is really dangerous. It's an addictive opiate. In fact, that's the physiological effect. So you would not want a racemic mixture if you're going to give this stuff to a kid as a cough suppressant. So, I mean, a few years ago, sort of one brand was taken off the market because it had some of this enantiomer in there. So just a subtle difference. And where's the chiral carbon? Here's one. And here it is over here. Just a subtle difference in the arrangement of atoms around a tetrahedral carbon can make a huge difference in reactivity. So we told some examples about drug design. And so if you end up with a larger molecule with several carbon centers, then there can be several enantiomers and things get complicated.